Hello, and today is Wednesday, March 24th. This is ECE 637, Digital Image Processing, and today we're going to do the Human Visual System. So I gave you the introduction. I took an informal survey before the class started about whether I'm going, because I feel like we're behind. We are behind. But whether we should go faster or whether people would prefer that I go faster or slower, and they said they like the same speed, which is not good because I got to go faster. So I'll try to go faster, okay? But what can I say? It's very interesting material, so you need to take the time to really enjoy it. So, okay, so the point is this. So we are going to, so the upshot is this. Oh, by the way, I just want everybody to know, yesterday I got my shot. So, hooray! Yeah, okay. I'm sure you really care about that. Maybe you would have preferred, if depending upon how the exam went, you may have preferred a different kind of shot. But anyway, okay. Anyway, no, exam's fine. A few people have emailed me with anxiety. You know, anxiety is part of life. It's fine. You're fine. Everybody's fine. Here's the thing: if you didn't do well on the exam, you know what you should do? Two things. Guess. One of them, I think, should be pretty obvious. Come on. Well, study for the next exam, but particularly, what would be a subcategory of that? So if you did badly on the exam, what should you do?
Well, obviously, we don't know what to do.
You have absolutely no idea what to do, okay? Oh my goodness. Okay, just a minute. Okay, I have to write something on here. Common sense. Huh?
You can't learn that, though.
You can't learn common sense? No, but you can practice it. They say common sense is not always so common, okay? Common sense. Okay, you can take that off of here because I don't want to hurt people's feelings too much. Just a little bit. Okay, so here's the thing. So what should you do if you didn't do well on the exam? Study, right? Okay, and particularly, what should you do? Oh, come on, guys. You're killing me.
Review the things you didn't understand the first time.
Review the things on the exam you didn't understand, right? I mean, guess what? Students don't do that. Go back and study those problems that you got wrong. Make sure, don't just say, oh, you know, it's gone, it's water under the bridge. It's not water under the bridge. Go back, swim it under the bridge, find the water, understand the exam. You need now you got a beautiful situation where you can go back, you know the problems you got wrong. You must have some point of confusion about, right? Or there's something, even if it's minor. You need to go back, study. The solutions are posted, right? Everybody knows where the solutions are? They're on the webpage. Study those solutions in detail because that's a learning moment, right? You have that whole thing in your head for 2 hours. You were under enormous stress. You were panicking, trying to do the problem. So you really have that imprinted on your brain. Go back and make sure you completely understand those solutions, right? I mean, it's wonderful. It's in terms of return on investment, it's the best thing it's the way you can spend your time. Okay, and then what's the other thing you could do? That's not so obvious, maybe. The other thing you can do is make sure you do all your labs, okay? You turn all your labs in. If there's something, if you really screwed up a lab, you can, when Reed's a nice guy, you can make corrections and resubmit. Don't torture him with 50 resubmissions, but you know, if you screwed up a lab and you want to fix it up, you can do that. I will be the course is graded on a curve, okay? All real graduate courses are graded on curves, okay? Because these are all difficult problems where even if I was taking my exam, I would not get 100, okay? I'm afraid to tell you what grade I'd probably get, but I wouldn't get the highest grade in the class because there are tough exams. So therefore, I make accommodations by curving, okay? But I'm much more accommodating if I see people have done the labs, okay? So I want to see that everybody's done the labs because that indicates to me that you made an honest effort. If I see a person who did really badly on the exams and they didn't hand the labs in, oh, That doesn't make me happy, okay? That doesn't make me happy. So do the labs, right? Obviously. Two things. Go over the exam problems that you got wrong and do the labs, okay? And then don't panic. You're fine, okay? It's a good experience for you. Life is, you have to go through these things.
The life is hard.
The labs are hard?
Life.
Life is hard. Yes, it is. It is. And that's a good thing. It makes it, there's a certain amount of enjoyment that comes out of the challenge, okay? So you take it in stride and you try to enjoy it, okay? That's my life lesson for the day, okay? All right, any other questions about that? Okay, now, so we're trying to learn about the human visual system, right? So, and if you're worried or something, send me an email. Sometimes it goes to my spam box, so I have to find it. So it takes me a little while to find it. Okay, okay, now what's going to happen is that we want to quantify the human visual system. And the human visual, we're getting some interesting phenomena on this, huh? It's like it's doing some kind of nonlinear oscillation on the text because of the background contrast. Interesting. So so what happens is we present a dot in a gray field, okay, and we show it to the observer, okay. Now you have to set up this experiment in detail, and I won't go into that right here. But basically, what you do is you present the dot. Sometimes you present the dot. Sometimes you don't present the dot, right? So let's say, you have like I'm just making this up. So you present the thing for like a certain amount of time. Let's say 100 microseconds. 100 microseconds is a typical time to present something like this because it's the amount it's the right amount of time where if you present it for too long, your eyes will move around. Okay, so if you present it in 100 microseconds, you get fixation of the eye. So, by the way, how many people have ever? I got glasses. Okay, so I go to an optometrist, an optometrist, or you can also go to an ophthalmologist, and they do a test. One of the tests they do is to make sure that you're not having problems with deterioration, at least for people my age, of the retina and the peripheral vision, and they flash these little dots up. Okay, typically they're Gaussian dots that are modulated. Okay, you can see them; they're little sine waves. Okay, I think so that they get a little bit of spatial frequency response going. So, and they flash the little dots up, and then they give you a little button to push. Has anybody ever done that? It's a standard piece of equipment. And then if you see the dot, you push it. If you don't see the dot, you leave it in. So they calculate like what percentage of the dots you're able to successfully detect. Now, it could be a random detection, right? So you have to do some statistics, but you set a threshold, okay? And you say if you're able to detect 50% of the dots, okay, roughly speaking, you have to set a false alarm rate too, okay? But if you're able to detect 50% of the dots, then you say it's a just noticeable difference. You're just on the threshold. Like when you see that dot, you say, I think I saw a dot. I'll push the button. But I'm not really totally sure, okay? You're right on the boundary between being able to see it and not being able to see it, okay? So you adjust the contrast, you adjust the difference in brightness of the dot relative to its background until you can just barely see it. And that's called the just noticeable difference. Now, here's the thing that's kind of interesting. So let's say you imagine you say, well, I want to be able to predict how much difference in the dot. Now, I'm going to quantify the dot by the energy. So obviously the energy has to be normalized by some factor. So it could be the energy per stir radian, okay? Because if you have to normalize by the distance of the dot from your eye, and then the actual amount of energy coming. If the dot is like is brighter, but it's further away, it would be hard to see. You have to do various things like that. So you have to do various normalizations, which I won't go into that. That's called that's an entire science of photometrics. Okay. But assume that the dot is of uniform size. It's like 1 inch. It's held a specific fixed distance away, 2 feet. So everything is is fixed, okay, except for the brightness of the dot. And then you just vary the brightness of the dot, and you measure the brightness of the dot in energy. And if you recall, coming back to here, you have some kind of mysterious curve that I never really described where it came from. And that mysterious curve tells you the spectral sensitivity as a function of wavelength. So when you calculate this value of y, the way you calculate it is by integrating the energy over the wavelengths and weighting it by I, okay? Now, so that leaves y. Now, ideally, the spectrum of the light coming from that dot will be constant, because you won't want to vary it. By spectrum, I mean the relative spectrum. So what you would call the color. We'll talk about color later. It's much more complicated. But the spectrum of the light is constant. You just vary the overall amplitude, okay? So then you change y, okay? Now, here's the question. If I make the difference in y, so there's going to be some background y. This is y sub b, and there's some y, right? Y, okay? If I make the dot y and I make the dot y sub b, okay, now if y equals y sub b, will I be able to see the dot? No, obviously not, because they're indistinguishable, okay? Now, if y, let's say then I say, okay, I have delta y is equal to y minus y sub b. And we'll assume that the dot's brighter than the background. It doesn't have to be, okay? So now the question arises, how big does delta y need to be in order to be able to see the dot at a just noticeable difference, okay? Now, here is what they call a Gedanken experiment. I think Albert Einstein created this concept of that you sort of, rather than actually performing an experiment, you just imagine what the outcome would be if you did perform it. So, okay, you have experiment 1. You're in a dark room. Y sub b, y is 1.1, and y sub b is 1, whatever the units of y are, okay? But they got to be proportional to energy. So delta y is 0.1. Then experiment 2, you bring the piece, see, if you take this piece of paper here, okay? This paper's sort of gray, right? You can see it's gray, right? It's kind of gray, okay? So inside, let's say in a dark room, or a relatively, if we turn the lights down in this room somewhat, it'll be gray, right? If I take it out on a super sunny day, it's like one of those really intensely sunny days in Florida on the beach, okay? And you take this piece of paper, it will still look like a gray piece of paper, right? But the actual light, if you took a physical instrument and you measured the light being reflected from the paper, on that sunny day, it's like 1,000 times the amount of energy being reflected, because the sun's so much more intense as opposed to in a dark room, or maybe not completely dark, but a not well lit room, right? We still see them both as the same piece of paper. But outside on the bright day, the actual physical amount of light being reflected is 1,000 times larger, okay? So now, but somehow we make the dot so it's only 0.1 larger than the background. So in this case, it's the change in the dot is 1 part in 10,000. And in this case, the change in the dot is 1 part in 10. This is a 10% change. This is a 0.01% change, right? Which dot do you think is going to be easier to see? Yeah, right? It's just intuitively obvious. So, if someone applies a pressure to my finger, okay, and it's a very delicate pressure, so the change in pressure is 10%, but it's very, very light, okay, versus having a gigantic force applied, but I only changed the force some very, very, very small amount. It'd be very hard to detect the difference, because your perception of a stimuli, your perception of stimulus in general is proportional. Okay, you're sensitive to the fractional change, the percentage change in the stimulus, right? It's fundamental to human perception. Okay, and it's not just true for light and color. It's true for sound. It's true for force. It's true for anything. Okay. So you can detect a very, very, very quiet noise in a quiet room, but that same quiet noise you wouldn't hear if there was if you were playing rock and roll in the background, because it's the percentage change that's important. So the point is this: if I want to quantify the just noticeable difference, we say delta y j and d. This thing will be a strong function of the background brightness. If the background is very, very, very bright, then I'll need a very large delta y to produce the just noticeable difference. And if this is very, 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 very dark, then I may only need a very small thing, okay? So that brings us to this concept of Weber's law, okay? So Weber's law says that it's not the change that's important. It's the fractional change. It's what is called the contrast. So the contrast is defined as the change divided by the background. There are different ways you can define contrast depending upon the context, okay? But for this problem, that's how we'll define it. So the contrast is this, okay? So contrast is a relative, it's sort of unitless. It's a relative term. It's between 0 and 1. It could be greater than 1. Well, it's hard to be greater than 1. Well, in this case, in the definition, it could be greater than 1. Usually it's between 0 and 1, okay? So that's called the contrast. Now, hopefully, the concept is that your ability to detect something will be mostly a function of contrast and will be generally invariant to other things. So the word invariant, okay? Invariant means that something doesn't change as a function of something else. So it's important to be able to say in the life and in world and in research, when something doesn't change with respect to something else, because it's a dependency you can drop, okay? So the hope is that when you use the contrast, the just noticeable contrast will no longer be a function of the background luminance, YB, okay? So it'll be invariant to it. And now, it's often intuitive. So just noticeable contrast, the just noticeable contrast might be, say, I don't know, 10%, or it might be 1%, or it might be 0.1%. But it'll be some fixed fraction, and that fraction will tell you how much change you need, how much percentage change you need in order to be able to detect this thing. Now, it's often the case that the more useful quantity isn't just noticeable difference, it's sensitivity. And sensitivity is 1 over the just noticeable difference, the contrast. So intuitively, if you only need like a 0.1% change in order to be able to detect something, right? You're very sensitive. Well, you're very sensitive, okay? That's what the word sensitivity means. The instrument is very sensitive if a very small change can be detected, right? So sensitivity is 1 over the just noticeable contrast. And okay, now what will happen is that, so you can plot then, so Weber's law, I'm going to just draw this rather than use the slide because it's more fun. So Weber's law is like this, okay? Over here, so this axis can be lots of different things. But in this particular case, it's going to be the background brightness, okay? And our hope would be, and over here, this is the sensitivity. So the sensitivity is equal to 1 over the just noticeable contrast. The just noticeable difference contrast, okay? So increasing sensitivity means you're more sensitive to something. So what will happen is Weber's law would argue that you're like this. Okay, I'll put law in quotes because most physical laws are only true in some realm, right? So they're kind of laws, but they're, I don't know. It's something about the word law that actually suggests that something isn't always true, okay? So for example, the laws of motion, right? Like what's his name? Sir Isaac Newton's laws of motion. They hold in some realm, but if the particle's traveling near the speed of light, then it's not true. Okay, so it's the same thing with Weber's law. That okay, now if the thing is really, 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 really bright, eventually what'll happen is that if the light is brighter and brighter and brighter, 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 right? And have you ever been out on a really, really sunny day, okay, and your eyes start to hurt, right? That happens to me. And you have to put sunglasses on or something like that, right? And imagine that you were like, I don't know if you've ever, when I was a kid, there was a TV show called Lost in Space, and they were like traveling to distant planets or something like that. And then, they'd have like two suns or something like Star Trek. And it would be like so bright you couldn't even look at it, right? So so eventually, if you get bright enough, eventually when it's happening, is this thing starts to tail off. Because you could eventually do damage to your eyes, right? But now the other thing that happens is you get darker, 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 darker. Eventually you get down to the photon limit. So the difference between, they say that humans can actually detect single photons. And statistically that's true, but not with a high reliability, okay? So if it's super, super dark and you make it twice of super, super dark, well, let's face it, it's still just really dark because you have a lot of photon counting noise. So what happens is there's essentially a noise floor. So what happens is it kind of goes like this, and then it tails off like this, okay? Now, the thing is that we mostly don't care about this. Don't care. Okay? But here we care. We mostly don't care about this part here because under normal circumstances you're not exposed to such intense brightness. Okay, and particularly for consumer items, like if you buy this iPhone or something like that, you don't have to worry about the display being so bright that it's going to blind you. It's just not a practical issue. But you do have to worry about if you're in a dark room or even if you're in a bright room and then it starts getting very dark. Okay, so that is relevant. Okay, so Weber's law approximately holds, but not exactly. Okay, and okay, so now here's the thing. Okay, perceptually uniform units, coordinates. So the problem here is that you have Y. This is energy. And let's say, okay, we're going to put these into digital systems, right? So this is Y in and Y out. Now, so in digital systems, you have to quantize things, right? Unless you're going to use floating point representation. But let's say that we're going to use 8 bits. So 8 bits is 256 levels, going from 0 to 255, right? So it's going to look like this. Right? I mean, I'm not drawing it very well, but you understand what I mean, right? So it's not a perfectly smooth thing because you have discrete steps, right? So this thing here, that's delta Y, okay? And of course, the input is 1. Okay, so can I see quantization error? Can I see the quantization error? So this is a Gedanken experiment. Now, if the quantization, if I use, I don't know, instead of 8 bits, maybe I use 16 bits, or maybe I use 24 bits, or I use 32 bits. If I make enough bits, eventually I'm not going to see the quantization error, right? And it's going to depend on a lot of things. But let's say that we have an image and it looks like this. Okay, we make an image, and over here we make it dark and bright. So I don't even know how to draw this, okay? I guess I'll draw it by drawing like this. And it's a uniform, smooth gradation from dark here to light here. It's a pretty boring image, okay? But this is a beautiful image for seeing quantization error. Because when you have these very smooth gradations, then you'll notice when you have a little edge, because what'll happen is it'll just go up and up, and then it'll bump up, right? Just a little bit, and then you'll see that edge all the way down the screen, right? You can actually see this. If you actually get a basic screen with 256 levels, and you put a gradation, in say MATLAB, you create a smooth gradation, okay, and then you'll see where it jumps, okay? You can see it. So 256 levels is not enough to make it impossible to see. These are called false contours. Contours. Is that how you spell contours? Contours. I think I spelled it better that time. False contours. That's a better spelling. There was a time when there were multiple accepted spellings for words in English, but I guess that time is mostly past. So there are going to be false contours in here, okay? Because of the quantization error. Now, will I be able to see these gradations, these contours caused by these jumping of gray level? Will I be able to see that? Well, we can go back and look at this idea of Weber's law, right? I'll be able to see it if it's above the just noticeable contrast, right? So are the contrast changes here the same as they are there? So if I go up one little step, how much am I changing the contrast here? Well, this contrast is changing by the change of the step divided by the amount of the input, right? So is the contrast change in these steps large or small? It's small, okay? This is small contrast changes. And over here, are the contrast changes large or small? They're large, right? Because here, at the first step, it's infinite. The input is almost 0, and then all of a sudden it went to 1. So I had an infinite change in contrast. And then the next time it might be like 100% change in contrast, or 50%. It's large, right? Large contrast. So, getting back, and by the way, this is super important. This is almost as important as knowing what the interpretation is of the GC frequency for a filter, okay? This is the second most important thing I'm going to teach you in this class. Okay? Where will you see the contours? You'll see contours in the dark area, okay? You'll see dark region contours or contours. You see why? Because here it's very large contrast changes, and here it's small contrast changes, okay? So what does this tell you about Y? Y is a blank choice for quantization. Is it a good choice? Excuse me?
Horrendous.
It's bad. Yeah, horrendous. So the answer is bad choice. It's a bad choice for quantization. Because if you take y and you quantize it, what's going to happen? Okay, so here's the official question. If you take y in units of energy that are proportional to energy, because y is proportional to energy, you quantize it with 8-bit quantization, and you display a grayscale sweep, what's going to happen? Everybody can say it in unison because it will be the answer to an exam problem, okay? You'll see false contours in the dark regions. So just remember that. You don't actually have to understand it. You could just like repeat it back in the exam. You'll see false contours in the dark regions, okay? Why? Because those are large changes in contrast, and these are small changes in contrast. So the question is, can we do something to fix this? Y is a bad choice for quantization, but what is a good choice for quantization? So we want a perceptually uniform. The problem is this is not perceptually uniform because the small changes here are very perceptually noticeable and the small changes here are not perceptually noticeable, okay? So what coordinates are we going to use that could fix this? Any thought? You take a log. Yeah, right. It may, because logs, you know, what happens, you know, if you take a bunch of adders or a kind of a snake, okay, and you wrap them, then you build a table out of wood, out of wood branches, okay, and you strap the adders on them. You go away for a day, you come back, you know what will happen? You'll have a lot, they'll have multiplied, you'll have a lot of them, because give any adder a log table and they'll multiply. Okay, I hope I can't be impeached for bad jokes. But give any adder a log table and they'll multiply, right? So what happens is that, oh, what was I doing here? Okay, yeah, so you take the log, okay? You take the log of y, and that we'll call that L. Okay, now what happens is, if delta L equals a constant, corresponds to like delta y over y equals a constant. It's a different constant, but you can calculate it, okay? So if I have a fixed step size in L, that will represent a fixed change in delta y over y, okay? And that, by the way, is equal to C, which is called contrast, right? So in this domain, if you believe Weber's law, that there'll be a delta L, J and D, and it will not depend on the background lightness. So if I change my coordinate system to L, then the false contours will go away. There's a problem with this, though. Okay, it's a good start, but it's a problem. So what are the problems with using the log? Excuse me?
So when the luminous becomes high, it will go down.
You're almost there, but you got it reversed.
For 0 intensity.
When it's 0, you'll have a problem, right?
Oh.
If the y is, I think you had the right idea, you just got it reversed. If y is 0, you're going to have a problem because L goes to minus infinity, right? So that's a problem. And you'd say, well, okay, we'll just have to make some accommodation for that. But it's more fundamental than that, because if you go back here, that corresponds to the fact that you think that the contrast sensitivity is flat all the way down to 0, but it's not. As you get down to really, really dark areas, then you can't take this whole Weber's law thing so seriously. Because so the log gets carried away in the really dark areas. But it's too extreme. And that exhibits itself by the fact that the log goes to minus infinity, which is unacceptable. We really would rather have something that's, goes from 0 to something that's positive, okay? Yeah, so now what happens is that we can go through some various mathematical arguments, which I do in the notes. You should look at those. But let me just make a motivational argument, okay? If I take, the log, log of y, okay, and I differentiate it with respect to y, everybody knows what that is. It's 1 over y, right? If I take y to the p, and I differentiate that with respect to y, I get p times y to the p minus 1, right? So if p is small, if p is, say, less than 1, okay, then this is p times 1 over y to the 1 minus p, right? Now, the p, don't worry about, okay? So, I'll do it a little bit differently. So I'll take y to the p times 1 over p, right? And I'll take the derivative of that. And then what I get is 1 over y to the 1 minus p. And I get that the derivative of log of y dy is equal to 1 over y, right? This tells you something really kind of fundamental, which is kind of interesting. And it comes up a lot, by the way, not just in this case. And this is probably something they didn't teach you when you were in calculus. The log of y, the log function, is sort of like the limit as p goes to 0 of, so basically, the log of y is sort of equal to, and sort of is very important in that sentence, because otherwise mathematicians are going to get mad at me. Plus, we'll have a constant as p goes to 0. So for small p, you can approximate log y by 1 over p. Oh, gosh, I can't believe I just wrote that. Okay, hold on. It's another example of me writing what I'm, not writing what I'm thinking. Okay, so it's 1 over y to the 1 minus p plus a constant as p goes to 0. For small p.
It's supposed to be y to the p, or
it's y to the. Oh, okay. Let me write it one more time. Yes. Okay. All right. I know what I mean. Okay. And the fact that you're correcting me means you know what I mean. Hopefully. So this is 1 over p times y to the p plus c as p goes to 0. Okay. Okay. So the point is that, and for also, this is true for y in the interval 0 to 1. I don't know if it's a good approximation outside of there. So the point is that you can sort of approximate log by 1 over p times y to the p. Okay. Now, the approximation is a little funky because as p gets small, what will happen is that, first of all, this thing is always positive, and that thing goes to minus infinity. So the constant is a strong function of p. Okay. So you have to fix p. But for a fixed p, this is reasonable. Okay. So p. So if you want sort of a version of log which is stable, you use this function y to the p, and you just make p small, and it behaves a lot like log. Okay, and if you think about it, a square root function. So this would be like log y. So this is 1. Right? That's what the log looks like. And let's take, and this is the square root of y. The square root is the same thing as the square, but it just turned on its side, right? So it's like this. Well, okay, you can see that, right? This function is sort of a little bit like that if you kind of adjust its position and so forth, okay, over some area, you know. So, okay, so what they do is they go, oh, we're not going to use, we're not going to, by the way, okay, so it's this derivative that's really the important thing. It's the derivative that's really the important thing, because the derivative is determining what the contrast sensitivity is going to be, okay? So what they do is they use, typically, for a perceptually uniform color system, they use L is equal to y to the p for p equals 1/3. So they take the cube root. This is the upshot. This is the theory. Now, what happened is that a lot of legacy in the imaging area is driven by the fact that early TV was analog, okay? And with analog systems, you couldn't really have that much dynamic range. And what happened, excuse me, is that if you take the cube root, you get something like this, okay? So it's y to the 1/3. This is very steep at the beginning. And in an analog system, it's very difficult to control offsets. So if you have just a slight error in where 0 is, you'll get really unstable behavior, okay? So this was not practical to implement in an analog system. And you can also make an argument that, you know, it's maybe just a little bit overboard, okay? So what happens is that they didn't use 1/3. The practice is that they use L equals y to the p, where p equals, okay, and this is like crazy, 1 over 2.2. And that is universally encoded in digital imaging systems, okay? So your TV set uses this, your computer display uses this, the iPhone uses this, the JPEG encoding uses this, everything uses this, okay? It's called gamma correction. And it's baked into all the standards for image coding. So when you take an image and you JPEG decompress it, let's say you get an achromatic image, so you get a black and white image, okay? You JPEG decompress it. People think what they've got is, well, first of all, they don't even think about it. They don't even think, like, what is it I have, okay? They don't even ask themselves that question. It's too philosophical. They go, well, I have an image. I'm like, yeah, fine, you have an image, but what the heck does it mean? Like, what do the pixel values mean? They're between 0 and 255, but what do they mean? Well, then the next thing they usually think is they go, well, I guess it's proportional to the sensor output, okay? Well, the sensor output is in photons, because the CMOS detectors or the CCD detectors count photons, or they output voltages that are proportional to number of photons. And photons count energy, right? I mean, so each photon at a particular wavelength is a packet of energy. So if I have 10 photons, I have 10 times the energy, right? It's proportional to energy. So what is, then the JPEG decompressed image is not proportional to energy. If it was proportional to energy, you would get this. You'd get contours in the dark regions, okay? what you have is a thing called a gamma corrective. I'm going to skip through this, and I'm kind of going fast. So this, you can read the notes, okay? Almost everything uses 2.2. There's Apple always likes to be different. So there was a point when they had sort of standardized on 1.8. And what will also happen is you can go into the displays and you can change the gamma of the display, okay? And we'll see later, everything I'm telling you is a bit of a untrue. It's sort of truthy, but it's not really true, okay? So, because they're details, but as we peel the onion, we'll get down to the deepest layers. Eventually, I'll give you the exact formulas, okay? So, but 1/3 is to the universally accepted value of P that's best in terms of modeling the human visual system. It's not exact, okay? It's approximate, but it's sort of the widely accepted standard for the first cut at something that's reasonable. But that's not what they use. They use 2.2, and it's baked into all the standards, okay? Now, okay, and so if you look at it then, okay, so this is what the curves look like. And now you've solved the problem because 0 doesn't go to minus infinity, so that's good, okay? And 1/3, it's steeper than 1/2.2. So what will end up happening is that this thing basically says you're more sensitive. The 1/3, because it's steeper, it's essentially saying that you're more sensitive to small changes in brightness and lightness at dark areas. Okay, and the 1/2.2, it's still saying you're more sensitive at dark areas, but the sensitivity is not as great as so as you increase P, as you decrease P, you're essentially assuming a more sensitive model in dark areas. And then in the limit, as P goes to 0, you have the log, which is the most extreme case, okay? And reality is somewhere in between. So this is basically a fudge factor you can use to adjust things. But normally, like I said, when you're doing human visual system modeling, you'll choose it to be 1/3. But in most imaging systems, it's chosen to be 1/2. So that, you did the lab on gamma correction, right? The main takeaway for the gamma correction lab is that I want you to come out of this class and realize that when you decompress an image from JPEG, or you get a PNG, or you get any other kind of image format, those pixels are not proportional to sensor output, okay? Which is part of a larger theme in this class. We have this idea, like particularly people who haven't taken signal processing, like, okay, we won't name who those are, but that we have this idea that you have a sensor. And then the sensor goes into an A to D, and then it goes out, and then you have like a display. All right? And there, over here might be the internet. Okay? This is untrue. Not true. Okay? Why is it not true? It is not true that you get a sensor, you get the data, and then you put it in the display and you get an image. That is false. Okay? It's untrue. It doesn't work. Okay? And it's sort of our own fault because the signal processing people have been so good about making all their algorithms so turnkey that they look invisible, okay? That you're like, well, the camera has a good, Apple told me it has a really good sensor here, okay? That's why the pictures look so nice. No. Well, I mean, it plays a role. You need a sensor. That's Steve Wozniak's signature, by the way, right there. It says Woz, right? You think I'm making it up? It's true. Okay, so that, so you go, oh, because You need a thing in between called computation. One of my exam questions, that has to process it. So if the sensor is not enough. You need to take the output of the sensor, you need to process it to make it into the thing that actually looks like an image, okay? If you took the RGB output of an RGB sensor, it wouldn't produce an image that looked good. Okay, I have to say goodbye now because I'm out of time. Bye. Okay, but here, I just have to